Good morning, everybody. My name is Wayne Harris, and I want to welcome you to today's training seminar. This is a seminar to introduce you to the TermPro enclosure design software. So I am going to be recording this meeting. I just wanted to let you know that. Mostly everything is just going to be the stuff I'm showing on the screen. This is an introduction to the program. I'm going to start out to just show you how easy it is to design an enclosure. Then we're going to circle back and focus on some of the details. Finally, we will take a short break and then we'll finish up with the question and answer seminar. So let's get started. I'm going to go ahead and share my screen. The first time you open the software, this is what you're going to see. This is the driver library portion of the program. The software comes with over 1,000 drivers already entered and ready to use, but you can also add your own drivers if there's something that is not included in the library. So for a quick demonstration, I'm going to just use this JL audio sub. The second thing you would do is you click on Enclosure Design and select the type of box you want to design. In this case, I'm going to select a plain vented enclosure. I then recommend that you click on one of the three profile buttons down here at the bottom of the page. These are listener profiles. They're labeled flat, normal, and boomer. So you would select the type of design that best suits your customer. In this case, I'm going to select flat. And the program is going to design an enclosure and tell me what the design volume should be, 2.66 cubic feet, tuned to 24 hertz. You don't have to use these parameters. These buttons should be considered just a starting point. I could change it, for instance, to click on normal. When I click on normal, now the box volume drops to 2.1 cubic feet, and the box should be tuned to 26 hertz. So for simplicity, I'm going to round these numbers off. So I'm going to change the design volume to 2 cubic feet. When I do that, notice the little padlock. When that padlock comes on, that means that since I entered this value, the program is going to try to maintain that number and not allow it to change. So I entered 2 cubic feet. The program then told me that that box ideally would be tuned to 27 hertz. And then it would show me the predicted frequency response right here. But just like the box volume, I can also adjust the tuning frequency. And one of the challenges, as we're going to see, is whenever you design a vented box, especially in car audio, it's difficult to tune a small enclosure volume to a really low tuning frequency. So to make things easier and also to give us a little bit of a bump in the bass response, I'm going to raise this tuning frequency to 32 hertz. And notice as I change the tuning frequency, the program shows me the new adjusted frequency response. Now, if I did not have this padlock locked for the enclosure volume, that number would change as well. So as I change this to 32 hertz, you'll see that now I have a nice 3 dB bump at 41 hertz. And I'm going to come back and show you the details of each of these pages in a few moments. So once we're happy with the design, the next step would be to design the vent. So I click on the Vent Design tab. And by the way, in TermPro, we normally run the program the same way you read a book, from left to right. That's not always possible, but for most cases, you want to start on the left and then move to the right. So on the vent design page, shows me my enclosure volume here of 2 cubic feet, the tuning frequency of 32 hertz, and then it defaults to a circular port 3 inches in diameter. And then this bar graph here shows me the vent air velocity. That's how fast the air is moving inside the port. I'm going to change this for now to 4 inches, and then we're going to move on. The next step is to click on Wood Design. The program supports 3 different extruded shapes, so rectangular and 2 different shaped wedge boxes, which I'll show you in a minute. So the default enclosure, and I'll turn on this so you can see what the dimensions are going to be. The default enclosure is what we call a golden box. That means the dimensions are selected to minimize standing waves inside the enclosure. But a lot of times when you're doing a sub box, the wavelengths are so long that you don't need to worry about standing waves inside of the enclosure. What you would typically do at this point is you would enter your critical dimensions and the program would calculate the unknown. So right now the defaults are 17.5 inches high by 10.6 inches deep by 27.5 inches wide. Let's just pretend for a moment that the maximum height we could use is 15 inches. So I'll enter 15 inches. When I do that, again, the little padlock shows up. Program knows that since you typed in that value, you really don't want that number to change. When I do that, the program's now going to calculate 2 new values for depth and width. Now, the next thing I'm going to do is, let's just say that for this box, we can only go 24 inches wide. I'm going to enter 24 for my width. And when I do that, the program's going to tell me that the depth now needs to be 14 inches. And this is assuming we're using 3/4 inch wood, which I'll show you how to change the wood thickness in a moment. So now here's what we have. The design volume's 2 cubic feet. The driver displaces 0.1 cubic feet. The vent displaces 0.09 cubic feet. There's no bracing. The total required volume is 2.19 cubic feet. And these are the dimensions necessary, the external dimensions necessary to achieve that design. And by the way, the program also supports metric. So I'm using English units because I'm stuck in the past century. If you decide to use metric, all you need to do is click on the little metric button on the toolbar to switch it to metric mode. So if we're happy with those dimensions, the next thing we want to do is place the hole for the vent and the driver in the box. So in this simple example, I'm going to click on hole. I select the hole shape is circular, and I can preload the dimensions by, like for the driver, if I click on driver, tells me what the diameter of the hole needs to be. It shows me my depth of the driver and what the surround height is. I then click on the place button, select the panel where I want the driver to be located. So I'm going to select this panel here. And then you can use these arrow buttons here to move the driver around on the box. And here's a really nice feature. I'm going to switch the view to the right-hand side. And then I'm going to hide that panel so we can see inside the box. So I come over here to panel visibility and uncheck it. And now I can see inside the enclosure. So this right here is representing the driver. And this is a really great feature of the software because it allows you to determine if the driver is going to impact, for instance, the bottom of the box or the back of the box. This is especially important if you're doing wedge boxes. I'm sure at one point or another in your installation career, you've designed a box and found that when you put the driver on the front baffle, the magnet's hitting the bottom of the box or the side of the box. Or even if you're doing a vent, the vent might be too long. But for this simple example, you can see that we don't have any problems with clearance. So you can also make the program show the box in a transparent mode. That's also useful. Once you're happy with the driver placement, you click on Done, and it will show you a preliminary placement for the driver. Now, the reason it's not finalized is because in a bandpass enclosure, you sometimes need to move things around so that the vent doesn't actually impact either the surround or the magnet structure. So now that we have the driver placed, the next step is to place the vent. So I come down here and I'm going to preload the vent dimensions. So I click on vent. Now it tells me 4.5 inches. That's because we have a vent with a 4-inch internal dimensions, but the PVC we're using has a thickness, so the total hole size is 4.5 inches. And it needs to be 13.477 inches long. And then the surround, it has a little bit of a surround for the flange, if there is a flange. So now what I'm going to do is I click on place. Again, you select the panel where you want the vent to be placed. Use the arrow keys to move it around. The vent or the driver, whenever you place a hole on the box, it just defaults to the center of the panel that you selected. So if this is what we want right here, we better check the clearance. So I'm going to click on the right side, and then I'm going to hide that panel. And that is really, really close. Actually, a little too close for my comfort. So I'll get into more detail on how to resolve this when we do some specifics. Essentially, you can move the port outside the box a little bit. You can place it on a different panel. Like I could put it on the top. Let's just do that. So I'm going to click on X to X out of it. Now I'm going to select place. This time, let's put it on the top of the box. And let's see what the right-hand side looks like. Now you can see what I was talking about. We got the driver is impacting the vent. I'm going to move that vent to the right. And you can see how far you're doing it. You select the top view. Let's just make it something like that. Again, we really are getting close. There is clearance. My rule of thumb is to always keep at least half the vent diameter distance from the back panel or an adjacent wall. It's not always possible. This is definitely not 2 inches, but I think it would still work. And for this quick down and dirty example, we're going to leave it alone. So I'm going to go ahead and close this back. I'm going to put it back to this. We're going to say we're done with the placement of the vent. And now we come over here and you click the finalize button. And when I do that, the program will punch the holes in the box. Now, you want to always look at how the box is assembled. The software is really smart about selecting the assembly is done in a way to minimize fence movement. And for instance, if this was a bandpass enclosure, all of these internal panels would be the same as the external sides of the box. You can explode the box just to see how it fits together, so you can figure it out. Really nice and helpful when you're doing a wedge box. And we'll do a wedge box in a minute when I get done with this easy demonstration. So if you're happy with this design, the final step is to come over here to the fabrication panel. The fabrication panel will allow you to print blueprints for each of the panels. You select the panels through this selector right here. This is the top panel. It shows you your dimensions. It gives you the hole details. So this is H2, and it tells you where the centers are. The centers are from this origin right here. So it's 6 inches in and 6.3 inches up, and the diameter of that hole is 4.5 inches. And it does that for each panel. And as you click on these panels, it will tell you the name of the panel and how many of them you need to cut. It will also show you your table saw blade angles, which on a rectangular box are all going to be 0. When we do a more advanced design here in a minute, you'll see that this is a fabulous tool right here. And then for your sides. So back panel and side panel. If you're happy with this, you can then print these blueprints. So you just click on the print button, and then it will let you select the printer. A lot of times I print to a PDF and then I save it. And that allows me to email it directly to the fab shop or to your customer. Or if you have a fancy printer that the software has trouble printing to, you can actually print a PDF that way. In addition, if you have a CNC cutting machine, like a CNC router, you can export the design to all these different CAD formats. So this is nice if you have one of those machines, you can export it, and the cutting machine can import it into its own software. A lot of times those software applications have optimization algorithms, which will minimize the waste. We're primarily focused on minimum fence movement when we use table saws, because if you're off just a hair, even one saw blade width, it can make the box not fit together perfectly. So that is how easy it is to design a program. You can also save the design. If you're happy with it, you just click on save, and click on save, and that's all there is to it. Now, I can get in there and design a box in 1 or 2 minutes. As you get experience with the software, you're going to find that it is really easy to use, but also very powerful. My suggestion to you is do not start with a 3-chambered, 6th order, isobaric, multi-driver installation. You need to start off with something simple, like a vented box, or a seal box, just to get a feel for how the software operates, and then you can work up from there. So now let's go back, and we're going to go into a little bit more detail for each section of the program. So we're back on the driver library page. Again, this is your drivers. They're listed here alphabetically, and they're sorted by brand name. So we have these little buttons at the top of the screen that are A through Z, or you can show all, favorites, and then you can also filter. Filter is really powerful. If you click on filter, you can enter any of this information. So if you want to find, let's say we're interested in subs with a diameter that's greater than or equal to 12 inches. You can punch that in, and you could say, you know, with 2 coils and 2 ohms, and that can handle at least 1,000 watts. So we need to click over there. Now I'm not going to do this because I want to use this JL sub. But anyway, you get the idea. Once I input these parameters, as many as you like, when you click on apply, the program will look through its entire database of drivers, and it will find the subs that meet that criteria. Another thing that is very useful is most people only work with a handful of subs. Maybe it's the brands you sell, and even within a given brand, maybe you only work with a few drivers. You can create favorites from the library. So one thing you can notice is you can see here that JL driver I was using is green. That indicates that I've tagged it as a favorite driver. So to tag a driver as a favorite, you just select it, and then down here on the toolbar, you can see where it says fave. Right now, that means it's a favorite driver. If I unclick that, it will no longer be a favorite driver. And they can be different brands, actually, or even you know, different subs within the same brand. To see your favorites, you just come over here and click on the favorite toolbar button, and you'll see the 2 drivers that I have in there for my favorites. So once you select a driver by clicking on it, the program will show you all of the driver parameters in this area right here. Anything that has a white background was entered and is part of the driver library database that comes from us. If it has a yellow background, that means that the parameter was not provided in the database, and that Term Pro is extrapolating those values. And it does a really good job of extrapolation. In fact, it's probably better at extracting these advanced parameters than the companies are at measuring them. So the third color is red. And if you see a field with a red field, that means that the field is questionable, that Term Pro doesn't believe the number that's entered. Now, the places where I see this usually have to do with displacement, especially if you select a sub that's a very thin profile sub. The program doesn't believe that. So if the displacement's not large enough, the program thinks it doesn't believe what it's seeing, and so it just turns it red. These are things that you use for a sanity check, and just verify. If you see something red, you just need to verify either the spec sheet or ask yourself why it's red. So finally, when you select a driver, you'll see this bar graph right here change. This is called the efficiency bandwidth product indicator. And on the left-hand side, it says sealed. On the right-hand side, it says vented. And then you'll see this needle right here. This needle shows you what the driver's preference is for a particular rear chamber. So for instance, the further this needle moves to the left, the more that driver wants to be installed in a seal box. And conversely, the more it moves to the right, the more it wants to be in a vented rear chamber. So even bandpass enclosures are vented or sealed on the back side. So this is this tool here provides really good insight onto the type of application you should use. So does the sub want a sealed rear chamber or a vented rear chamber? Doesn't mean you can't put if it's over here, it doesn't mean that you can't put it in a vented box. It just might be hard to achieve a design when you do that. So you can also, as I mentioned earlier, you can add, edit, and delete drivers from the library. So there's a button here that says add. So if you have a driver that's not in the library, you can click on this add button, and then you input, at a minimum, you have to input all of the green parameters, the top half. So you have the name, series, and model number. Then you have the required parameters, which are all green. You have to enter those. Term Pro can't do any calculations unless this information is provided. And then down below, you have the advanced parameters. Unless you're absolutely certain that you know what these values mean and that the information provided by the manufacturer is accurate, I would not enter those. I'd let the program extrapolate the values. For example, and there's another complication here when entering these advanced parameters. So, and I will just tell you what that is briefly. Normally on a DVC sub, you'll see that the impedance is per coil. And in fact, if I hover over these fields, it tells me enter the advertised impedance for each voice coil in ohms. So in a DVC, if you have a 2 ohm, DVC sub, you'd enter 2. So each coil is 2 ohms. But manufacturers sometimes measure electrical parameters by wiring the voice coils in series. Not up here, but down here for the advanced parameters. That means they may list the RE with the voice coils in series, the LE with the voice coils in series, the BL in series. That causes a big problem if you input that when the program is expecting the value per coil and you enter the total value. It'll be twice as large and it'll mess up your calculation. So long story short, I'd recommend that unless you're really proficient with using the software, be careful about entering advanced parameters, with the exception of QES, QMS, and the some of these physical parameters like the depth of the driver and the displacement of the driver. Those are nice to have. And QES and QMS are related to QTS. If any of those three don't balance, you'll have a red field and you know you made a mistake. The program also supports dynamic swapping or switching between English imperial units and metric units as you're entering the parameters. For whatever reason, sub-manufacturers provide their driver parameters in a cryptic combination of English and metric units. So it'll ask you, you'll enter the driver in inches and the VAS in cubic feet. But when you get to the X max, it'll probably be in millimeters. So if you get to that point, you would then click on metric. Like for instance here, let's do a driver. I could enter 23 Hertz for the FS, 0.34 for the QTS. Let's do 2.7 for the VAS in cubic feet. Now, when I get here, you'll notice where it says X max, and in parentheses, it's in inches, IN. But I'm going to switch this over to metric, and now in parentheses, it says millimeters. So let's say this is 10 millimeters, and so on and so forth until you complete the job. Once you're done, you click on save. The program will add the driver to the library, and the information will show up right here. So that's all there is to it. The driver library is really nice and powerful. The good thing is most people only work with a handful of drivers. Once you have those in, you don't really have to spend a lot of time here other than selecting a sub. I will say this, if you're entering a driver, you need to do a sanity check at the end. Look at these numbers and compare them to what's on your spec sheet or on the side of the box or on the website, and verify that the information you have here matches the information on the data sheet. If it doesn't, you need to go back and check your values. Okay, so from here, the next thing you would do is you'd go to the Enclosure Design tab. Now, I did a quick box earlier, but I want to just briefly talk about these sub boxes. So it's really important when you're meeting with your customer to talk to them and do a consultation and ask some real critical questions. For instance, how loud do you listen to your music? What kind of music do you listen to? How much space are you going to allow me to use inside your vehicle? How much money do you want to spend? Are you restricted to a specific type of sub? Because sometimes customers have their own subs and they just want you to build a box. These are things that you need to ask because that will help you determine what type of enclosure you're going to build. Now, a lot of times when you're experienced with the software, it's easy to just use these two buttons right here to toggle back and forth between the enclosure shapes. And I'm going to go ahead and reset our design. But as I click through here, you can see the different designs. So it's just a shortcut. But you can also click on this select button, and then you can see all of the different types of enclosures, and it gives you a list of advantages and disadvantages for each enclosure type. So as you're doing your consultation with the customer, or even if you just want to reinforce your own knowledge of these boxes, you can go through this. So like, for instance, if I'm looking at a seal box, some of the advantages are it's easy to construct, it gives moderate to good performance, and it has good mechanical power handling. The disadvantages, it's less efficient than, for instance, a vented box, and the cutoff frequency, that's how low the box plays, is limited and doesn't play as low as a vented box. And you can go through and look at each of these types of enclosures and see what the advantages and disadvantages are. So you have built-in talking points right here on the screen when you're working with your client. And it also helps to legitimize you as an expert because they know you're not telling them a bunch of baloney because they can see what you're reading at the same time. Now, one of the things I like to do when I'm working with the driver is maybe do a comparison of different enclosure shapes or styles so that you can see what the performance characteristics are. So let's do that. Let's start with a simple seal box. The software supports up to 4 different designs at the same time. So I'm going to select layer control number 1. So our first design is going to show up on layer 1. I'm going to select my enclosure. So I selected a seal box. I'm going to come down here, and normally you just punch in like flat, normal, or boomer. Now, in a seal box, a flat design is going to give you a box that has the lowest cutoff frequency. Now, we use these terms like F3. F3 is simply the frequency where the output of the system, of the response, is 3 dB down with respect to the passband, this area here. And you can easily find that using a crosshair. So I'm going to turn off the grid so you can see. If I click and hold the mouse and move it back and forth, over here you'll see the frequency and the relative output level. So if I move this over at 3 dB, it's 41 hertz. And just like a miracle over here, enclosure frequencies, the F3HP is 41 hertz. In a seal box, you can't get this number to go any lower than a flat response. So if I make this box bigger, actually the cutoff frequency is probably going to go up. So for now, I'm going to just leave this box here as a flat design, 1.442 cubic feet. And let's turn our grid back on. Now let's compare that to a vented box. So if I come over here, I'm going to select layer 2. Now I have to select the layer first, otherwise it will change everything we just did. So I'm going to select layer control number 2. I'm going to switch to a vented box. And let's do the design we did earlier. So I'm going to specify a 2 cubic foot box tuned at 32 hertz. Now, here is the thing that I want to point out. This heavy green line here is the response, is the relative frequency response of the vented enclosure. This other green line is the relative response of the sealed enclosure. Look at all of the additional bass that we have right here. I mean, this is a massive amount of energy that is free. So it doesn't take any more power to get this output here than it does for the seal box. And remember this, if somebody's putting a vented enclosure, if somebody's putting a box in their car, the reason they're doing that is because they want more bass. I mean, let's be real. Nobody's going to put a sub box in their vehicle unless they want bass. This right here is going to give you a lot more bass. It's going to be audibly louder. Most people can barely hear a 3 dB difference in output level. And as you know, it takes 10 dB to sound twice as loud or half as loud. In this case, we've got a full 6 dB more output at 40 hertz. So at 40 hertz, this vented box is going to play 6 dB louder for the same amount of power. Or it can play the same loudness as the seal box and use 6 dB less power. So that's a significant power saving. So the vented box, it either gives you a maximum output level that's much higher, or it gives you the same output level for a lot less power. So you could use a smaller amp, or the amp doesn't work as hard. It's more reliable. There's less demand on the electrical system. So efficiency is always a big thing when you're doing these systems. You want to maximize output, maximize reliability, and you do that by focusing on efficiency. So Before I move further, let me just show you a couple of the other graphs. I'm going to hide the seal design. So I do that by unclicking the visibility tab for layer 1. It's still there. It's just hidden. And I'm going to hide the grid. And now what we're going to do is look at the power handling of the system. So I turn on the power. There are two types of power handling that we're dealing with in sub boxes, and we can control both of them to a certain degree. The first is the rated maximum RMS power handling of the sub. That's really designed in by the manufacturer. This sub has a 600 watt RMS power rating. And you can see on the right-hand ribbon that when you go above 600 watts, you're exceeding the electrical power handling of the driver. In a perfect world, this system would be able to handle the full 600 watts of electrical power without any mechanical limitations. Now, this heavy yellow line here shows us how much power we can apply to the system at any frequency without exceeding either the electrical power limitation or the mechanical power limitation. And you'll see there's this teeny thin yellow line here. I don't know if you can see it on the projector, but there's a thin line here and it goes all the way across at 600 watts. That means in a perfect world, you're not going to, a perfect world, this would actually be a straight line. And I bet you that seal box it is. Let's take a look. I'm going to turn on visibility for sealed. And you can see in the seal box, you have full electrical power handling across the entire graph. In the vented box, down here at 16 hertz, we start seeing some mechanical power handling issues. But it's at 16 hertz, and there's really no music down there. If you're really concerned, you could use a subsonic filter. But let's try to understand why that's happening. So to do that, I'm going to turn on this displacement plot. Now what we see is this magenta line. Now this magenta line is showing us the excursion of the driver's cone versus frequency for the applied power of 600 watts. At higher frequencies, you can see we have very little cone excursion. As frequency goes down, the excursion increases. At the tuning frequency of the box, we have a reduction in cone excursion. And below the tuning frequency of the enclosure, below the tuning frequency, you'll see a pretty rapid rise in cone excursion. Now, again, I'm not sure if you can see this, but this ribbon here, this magenta ribbon right here shows the X max of the driver. X max is a rating, is one of the teal small parameters. It's the maximum one-way linear excursion of the driver. It doesn't mean the sub's going to break if you exceed that. It just means that the driver's no longer linear. The voice coil is no longer in the magnetic gap where it should be. And if you do exceed it to a real great degree, you could actually cause a mechanical failure, like the spider could break, the voice coil could come delaminated, the surround could break. So we only use the X max as a limitation, and you'll see again, there's a real thin line right here that gives us an idea of where the X max of the driver is. And we can see as frequency goes down, when the excursion of the driver exceeds the X max of the driver, that is exactly the point where we start seeing these mechanical limitations in power right here. So your goal as an installer is first of all, you need to listen to the customer and figure out what they want. And then when you figure that out, you need to design a box that provides the best performance. So you want it to play as loud as possible, You want to make it as efficient as possible, and you also want it to be as reliable as possible. When a manufacturer publishes a recommended enclosure, it's just a generic boilerplate. They have no way, there's no way that their enclosures are going to be ideal for an individual customer. So they're usually designing boxes that are super conservative because the last thing they want to see is warranty repair. The same is true for you. You don't want to have to deal with warranty repair. So you need to pay attention to these power and displacement plots. If you pay attention to this, you can ensure that you're not going to design a box that will break. So now let's do a few more comparisons. I'm going to turn these guys off, and we'll leave the visibility on for the sealed enclosure. The next step is let's design a simple bandpass enclosure. And the way we do that is I selected layer 3, and you've never designed like a fourth order box this easy. You come over and you select the box. Fourth order box, sometimes it's called a sealed, is a single order bandpass enclosure. It's simply a sealed enclosure on the back of the driver and then a vented chamber on the front. And what I'd like to do again is you come down here, click on flat, normal, or boomer. Let's click on flat. The program will do the bandpass design for you. Let's hide those other two temporarily. You see, we have a really nice flat bandpass response. It's about 12 dB per octave on either side. These numbers here tell us information about the bandpass. So it's the high pass section is 27 hertz. The 3 dB cutoff on the high side is 62 hertz, and the box is centered at 41 hertz. Now, this is playing a little lower than we really need. So there's two things we can do here. And this is what I really love about Term Pro. So if I click on these buttons right here, the Q button changes the center frequency of the enclosure, but keeps the shape the same. You see, as I'm changing this, let's center this thing up. Let's change it to like 60 hertz. Okay, so now the center of this bandpass is 60 hertz. Now, why would you care about that? Well, first of all, there's a lot of music there. And now the 3 dB down point is at 40, and the high side is at 90. But if you're building a car, and let's say you do a sweep and you determine that that vehicle has a real strong resonance, say at 40 hertz, maybe you're doing an SPL car, you could design a bandpass enclosure that is, centered at 40 hertz. Now, why would you want to do a bandpass enclosure? Let's take a look and we'll see why. Again, there's pros and cons. You can one of the benefits is you can program the gain. So in this case, now this output is 4 dB higher. Let's see what our seal box looks like. Look at all of the additional bass energy right here. And this is a part of the spectrum where there's a ton of music between 40 and 90 hertz. Or maybe we even want to play it a little bit lower. Let's dial this down. Let's say we change it to 55 hertz. A ton of energy in this range, in this area right here. So you're getting a lot more sound without any additional power. Now look at the trade-off. You see now I'm only up 3 dB. So as I change things, I can see over here now it's changed to 4 dB. So there's these trade-offs as you adjust. There's gain bandwidth trade-offs here. And as you adjust it, you can actually see how that works. And I'm going to change this back over to 50 hertz, 55. There's a second parameter that you can change, and I'm going to go ahead and hide our seal box, and that's bandwidth. So bandpass enclosures have what is called a gain bandwidth product. This is how I like to envision that. If you imagine this green graph here as a solid piece of wire, and you take your left hand and you grab this side and you grab this side with the right hand side, the length of that wire is fixed. If you move your hands together so that they're closer to one another, this right here will peak up, so you'll get more gain. But the bandwidth, so think of bandwidth as the distance between your hands, gets narrower. So the product of those two numbers is constant. So as you move your hands together, the output peaks. As you move your hands apart, the output goes lower and the bandwidth gets wider. Let me demonstrate. You do that by using this term called S. So if I increase the S, you can see, and it might be easier to visualize if I turn off this auto ranging stuff. So now I think you'll be able to see. Okay, yeah, see, now you can see it without instead of the side, this auto ranging on the side. Now we can see that as we adjust the bandwidth, I'm making the bandwidth wider and wider. The output level is getting less and less. You can also go the opposite way, and you come up here. Okay, now we're looking at 6 dB of gain, but the bandwidth's really narrow. And when you start doing stuff like this, you start creating, if you start creating a box like this, yeah, it's going to have a lot of gain, but only at a very narrow range of frequencies. So you end up with a box that sounds like someone's beating on the bottom of a garbage can. So now it does have its place. If you're building a competition vehicle and you don't have a lot of power, or if you have a customer that only listens to a very narrow range of frequencies, you could design a box like this, and man, it would hammer for sure. But it would only do it within a certain range of frequencies. So I'm going to switch back here just to our default. Let's center this up again to 55 hertz. Now we have a box that has a little more than 3 dB of gain. Let's see how it compares to our other two designs. Pretty much smokes the seal box. In almost every case, unless you're designing for an audiophile who really doesn't want to hear any port noise, or they're just really concerned with transient response, the seal box is, or you have a driver. Some drivers are made, in fact, a lot of car audio drivers nowadays are made for small seal boxes. But even then, look at how much additional bass we're getting out of the vented box and the bandpass box. Now, the bandpass box has a little bit more gain output in this area, between 50 and 75 hertz, but the vented box plays a little bit lower. So depending on your customer, you would have to choose one of those boxes. Now, there may be other factors involved here. For instance, sometimes you may want to protect the driver from the environment. You don't want anybody to touch the cone or punch in your dust cap, or maybe this is a marine installation where you don't want any of the like water and stuff to splash on the cone. You might select a bandpass box for that. Or sometimes in a sedan, you might build a box where the enclosure is in the trunk of the vehicle, and then the vent actually couples the enclosure to the rear deck. You can actually, you can put the vent external to the box and use it to connect to the listening environment. So everybody has a reason. This is why it's important you talk to the customer and try to visualize, what are we trying to achieve? And then think of these enclosures the same way an artist would think of paint. So depending if you're painting a portrait or a landscape, the tools you select are going to be different. This is just goes in your toolbox. It's an arsenal of things you can use to achieve the desired objective. And then finally, just to for completeness, let's go over here and do a 6th order box. Now, a 6th order box is a vented rear chamber with a vented front chamber. These boxes are really complicated. You have to use a program really to get it right. They're very temperamental. You have to make sure that the driver parameters in the library, the advanced parameters are accurate. Otherwise, the results are questionable. In fact, this type of design is very unforgiving of design mistakes. So let's go over here. And again, let's start with a flat box. The program will come up with the initial design. One thing to point out, if you look on the 4th order box we just did, you'll see that both sides are symmetric. It's about 12 dB per octave on both sides of this response curve. On a 6th order box, however, the front side's about a 12 dB per octave roll off, and the high side over here on the left is like a vented enclosure. It's 18 to 24 dB per octave, depending on the tuning frequency. So it has a much steeper roll off. Now you can see initially that this 6th order box has a lot of additional bass over here. Now we can play around with that. One thing I know is that by adjusting the tuning frequency of that rear chamber, as I make the tuning frequency higher, it's going to create a bump here. But you have to be careful with the bandpass enclosure, because if you make the tuning frequency too high, it's starting to interfere with the cutoff on the right-hand side. So let's just, and this is the great thing about software modeling. And in fact, this is one of the reasons that I developed the TermPro program, is I got tired of building boxes and then trying to decide, or that you had to build them and then see if they work. And that got old fast. It's way more fun and a lot easier to come over here and just do what if scenarios. So let's do this. What if the rear enclosure was 2 cubic feet like we've been using? Well, one thing happened right away is it made the response of the bandpass a lot flatter. Now let's see what happens if we change the, let's do this. Let's change the front volume to 1 cubic feet. See what happens. Ooh, not good. When you get messed up, the easiest way is to just start over. And I got to unlock it. Change this to 2 cubic feet. See what happens if we change our tuning frequency. If you start messing around, you see as I'm moving the tuning frequency to the right, it's starting to have an impact on the output level of the system, because these two tuning frequencies are getting too close together. So anyway, you just have to play around with this stuff. Now you can see as I make the tuning frequency too low, it starts to affect the symmetry of the response. And that's why I'm saying these 6th order boxes are really temperamental. You have to play around with it. The program is really good. It actually has AI, if you consider putting me in the program as intelligent. But I came up with algorithms that it'd be basically like, okay, Wayne, what's a good flat response for a 6th order box? And this is what you're going to get. Again, these buttons are profile buttons. They try to determine, you know, they're trying to be representative of the listener. Now let's just compare the visibility of all of these and see where we're at. I'll turn on the grid. So now we have 4 different designs. I would say we nix the seal box. Don't like it. There's also going to be an issue of personal preference. These enclosures have a distinct sound. I personally prefer the sound of a vented box to one of a bandpass box, but that's a personal preference. If you're talking to your customer and they're playing rap and they like this artist and the bass tones are the same note, then a bandpass enclosure would probably be real suitable. I'm going to do away with the 6th order box because it's a lot bigger. You can see it's 2.6 cubic feet on the back, 1.3 cubic feet on the front. It's more complicated to build. You have 2 vents. So I'm going to just, in this particular case, I am going to hide the 6th order box. And now that brings us to these 2 designs here. A vented box, and then this 4th order bandpass. Both of them play about the same sound pressure level. They both have about the same relative output. The bandpass box has a nice flat response in the pass band, and it plays from about 40 to 80 hertz. This is a tough call. I mean, this is actually the bandpass box has some additional bass up here in the pass band. This is where you listen to music. Let's do this. For this design, since we haven't done it before, let's go ahead and continue with this 4th order box. So we're going to do the 4th order box for the remainder of our design. So at this point, I'm happy with this design. 0.6 cubic feet on the back, 0.8 cubic feet on the front. Let's just check the tuning frequencies. Tuned to 55 hertz, which looks good. So now let's come over here and do the vent design. The program does it does flange ports. And by the way, if you have access to these types of vents, this is by far the biggest thing you can do to improve the performance of a vented enclosure. I cannot even begin to tell you what an impact it makes. These flanges make an audible difference on the sound of a vented enclosure. They allowed the system to play a lot louder. I think that, if there's any one thing you can do, I definitely recommend using a flange. And by the way, you have to use it on both the inside of the box and the outside of the box. It also does pipes. These are the simplest types of vents to use. And then it does rectangular ports. Now, this is a rectangular port that sticks inside the box. Now, the program, the copy that you're getting here today or tomorrow, whenever you put it on your computer, it does those 3 types. In probably the next update of the software, it's also going to do slotted ports. So slotted ports are popular if you're doing the same design day in and day out. Makes a lot of sense. But for the most part, I prefer a flange port or a pipe. Now, when I talk to installers, a lot of times, let's just forget the slotted ports for now. They'll use a rectangular port because they don't have any PVC and they have a ton of wood. It's easy for them to build. But what I say is these types of ports are really difficult to fine tune. A pipe, on the other hand, is super easy. And in fact, here's what I would recommend. You start with a piece of PVC, you design your vent, and you make it 1 inch longer than the program's calling out. Then you test the design, you test the tuning frequency, and I'll talk about that in a moment, how you can do that. And then you can trim it down easily and get the tuning frequency exactly what you want. Because I'll tell you this, in a vented enclosure, box volume variations of 10 or 15, 20% have very little impact on the overall performance of the system. Don't really impact the design. But changing the tuning frequency, even 1 hertz or 2 hertz, creates a huge impact on performance. So when you design the box and you build it, you really need to test the tuning frequency. Now, as in a world where you're doing installs, you're not always going to be able to do that because you don't have a subwoofer that's fully broken in. Now, you might send the install out with the customer and ask them to come back in a day or two, but when the subs are brand new, they're not broken in, and the compliance, the rigidity of the cone and the surround and the spider are different than they will be 8 or 10 hours after 8 or 10 hours of use. So, but let's say when you're testing the vent, let's come back and cover that in a minute. I want to circle back. Let's just stay focused on the vent design for now. So one of the other benefits of a vented box using a pipe is you could experiment with converting the design from a vented enclosure to a sealed enclosure by using one of those. It's just a plug that's used for testing pressure of plumbing systems. You can buy this, like here in the US, we would buy it at a Lowe's or a Home Depot. It's a plastic plug. It has a rubber gasket around the outside and a big wing nut. You just stick it in the opening, turn the wing nut to tighten it up, and now, just like magic, you've converted your vented box to a seal box. So anyway, one of the things you'll want to do when you come over here, as I mentioned earlier, the program is going to default almost always to a 3-inch circular pipe. That is usually not the design that you use. As an installer, your goal when designing a vent is you want to make the port air velocity as low as you can get it and still fit the vent inside the enclosure. And that's a lot harder. That's easier said than done. And let me tell you why. When you have the vent design up, we have a 3-inch diameter, and it needs to be 5.5 inches long to tune our 0.82 cubic foot box to 55 hertz. The only way to get this number down to reduce this port air velocity, and that's what this bar graph here is showing you. It's showing you the speed of the air inside the vent. If this port air velocity gets too high, then you hear a chuffing sound when you're playing music. The port actually makes noise. And that's doubly important on a bandpass enclosure because think about it, all of the sound inside of the subwoofer enclosure is coming through this vent. So you really want to work hard to get this number down as low as you can. The only way to reduce the vent air velocity is to make the vent diameter larger. But watch what happens. So as our diameter is 3 inches and our vent length is 5.5, watch what happens as I start changing the vent diameter, the vent length starts getting longer. So as I make this thing a 4-inch vent, now the vent needs to be 10.7 inches long. So as the vent diameter gets small or larger, the vent length gets longer. And in some enclosures, now remember, this box is only 0.823 cubic feet. You start putting a big vent in a small box, that box has to get bigger. And you might end up with a case where your box is too big to fit in the customer's car. So again, what we want to do is we want to get this bar graph as low as possible. The colors are not absolute deal breakers. These are just to give you an indication of what's acceptable and what's not. you definitely want to keep it out of the red. It's not always possible. When you try to tune a small vented box to a low frequency and the sub handles thousands of watts of power, you just might end up with a situation where you can't get it below 11 or 12 or 13%. So as you make the vent area larger, the vent length gets longer, but the port air velocity gets lower. Now, watch what happens when I switch this to a flange port. The port length is really not going to change a lot, but the colors on the bar graph have different limits. You can see now for 7.1% Mach, it's in the green. Now, people have also asked, this length is different than what we're looking at before. The length is the length of the pipe that you cut. The overall length of the port is longer. These are usually 1.5 inches. So each end adds 1.5 inches to the overall length of the design. For simplicity, I'm going to switch back to a pipe. As I was saying, 10.76 inches long. So if we're happy with this, and by the way, you've seen me doing this earlier. These buttons on the right are used to control my view. So I can use these arrows to change the position of the camera for viewing purposes. You can turn the legend on and off. The legend is like, this is the diameter and that's the length. You can turn the grid on and off. You can actually toggle through different types of grids. And then you can animate it. This is cool, like if you just want a screensaver. You can change the perspective. This really serves no purpose for the most part. When you click on perspective, it provides a realistic viewpoint. So things that are closer look bigger, things that are further away look smaller. When you turn that off, it looks funky. You can also view a wireframe, transparent view. You can make it solid, or you could render it in a wood coloring or whatever you want. And then there's these presets here. So a lot of times the program defaults to the isometric view, which is that right there. So, and you can do a front view, top view, left view. These are just nice to get around. And then of course you can use the arrow buttons for exact control. So now that we have our vent design ready to go, the final step is to come over here and do our wood design. Now, for a bandpass enclosure, let's take a look at our design. So we have two chambers and they're shown, the details are shown here. We have a back chamber and a front chamber. The back chamber has a design volume of 0.61 cubic feet. The driver displaces 0.105 cubic feet. We don't have any bracing in the box. The total rear volume is 0.72 cubic feet. For the front chamber, the design volume is 0.82 cubic feet. The vent displaces 0.07 cubic feet. No bracing. The total volume for the front chamber is 0.896 cubic feet. The total volume of this enclosure is 1.616. This really doesn't serve any purpose. These are the values we're interested in. Now, the program's going to come up and give us these arbitrary numbers for the dimensions. Let's think about this. Let's turn on the legend so we know what we're working with. So we know, I'm going to hide that top panel. This is the partition where the driver is mounted. And there's almost no way that that sub is going to fit on this panel without hitting this back wall. But I wouldn't want to build a box like this anyway. So let's do this instead. Let's make our height 15 inches. There's our little padlock. And let's make, let's see, what do we want to do here? just for simplicity, you make it whatever you want. Let's make the depth 20 inches. It was almost 20 inches actually. So that tells me that the total width right here is 13.43 inches. We still might not be able to fit that driver on there. Let's take a look and see. So I'm going to hide the top. Now let's place the driver on there to see where we're at. So I'm going to come over here and click on hole. I'm going to load the driver. I'm going to click on place. I'm going to select the panel. It's the interior baffle. And let's see what it looks like from the top. Okay. You can see that there's no way that that's going to work. This is where the driver's mounted, but the magnet structure is sticking through the outside of the box. So this is not going to work. Let's change things up a little bit. I'm going to go ahead and cancel this. Let's turn on our panels. Let's go back to isometric view. So what we know is we need this width to be deeper. Now, this is something where you have to be careful. If I click in a value here, let's say I make this 20 inches. Now notice these other two dimensions are locked. So if I change this to 20, we're going to get a warning. And it says all of the enclosure dimensions are currently locked. If you continue, the enclosure design volumes, VB1 and VB2, will be updated to accommodate the new dimensions. Would you like to unlock these values? No way, Jose. We don't want to do that. We went through all that effort to get to this point. So let's go ahead and click on no. Now let's, program was smart and kind of knew what I was going to do. So I entered the height. We left the height alone at 15. The width, now we changed it to 20, and the diameter is 13. So let's see what that looks like. Let's hide that top panel. I can tell already this is going to fit. Let's just put the driver. The only thing we got to worry about here now is the flanges. And in fact, let's see what happens. So we come over here. Let's place it. Now I can't see it because this guy's in the way. So let's hide that right panel. I guess it's the left panel. Ooh, this is not going to work because this is the hole size, and you can see that it's actually going to impact. It won't impact, but the flange isn't going to work. So it's back to the drawing board here. And these are the things, this is the kind of stuff that you really need the software to do this. So let's do this. Let's unlock this. And let's change this to 18 inches. Now the diameter is 14.6 inches. If the driver will fit on that internal baffle board, we know we're good. I didn't mean to punch the hole in the box. Anyway, I already did it. So normally I was in a hurry and I clicked finalize. So anyway, we've already punched a hole in the box. Let's see 15 by 18. Let's do this. Because I wanted to do that. So we come over here, we load the driver. It's already loaded. We click on place. We select the baffle. Let's look at it from the top. Man, this dude is a challenge. we can see that we still have a problem. Let's go ahead and stop that and adjust our dimensions one more time. This looks like it's right on the brink, but you get the idea here. The thing that's nice about the software is you can do this to see what the problems are going to be. My guess, this is probably going to work. Here's a way we can find out. If we zoom in, let's look at it from the front. Let's hide this front panel. Zoom in. Let's rotate it. Let's turn it into a transparency. I mean, it's just like literally right touching. You could finagle these dimensions just a hair more and you would be okay. And in fact, let's just do that. Let's say we change this to 16, let's say 17. And well, I made it worse. Yeah, because I went the wrong way. Punched in the wrong number. Punch the right number in the wrong field. How's that? But I think you're getting an idea of the power of the software to visualize what's going on, what kind of problems you might encounter. Let's go ahead and see where we're at here. Let's hide that front panel. And make it transparent. I mean, we're right there now. So let's just say, you know, we're going to go for that. You could mess with this for another 5 or 10 minutes and get it perfect. I'm going to go ahead and click on done. And now when we look at the, you can see the driver's in the box. I'm going to finalize it. I'm going to do one more thing, guys. I'm sorry. I want to show you one more thing. So I got to reset this. And I'm going to tell you why. Last year, I did training seminar on sub-enclosure design for Knowledge Fest. So I did 4 seminars. And for that, I actually built these 4 types of boxes that we're talking about here. So not only I talked about advantages, disadvantages, design philosophy, et cetera, et cetera. And then I showed people how to design the boxes using the software. And then we actually listened to them. So in order to listen to them, I had to have the boxes manufactured. And so I designed the box and I sent it to a fab shop, and they called me and they said, well, where do you want on this these bandpass enclosures, where do you want us to put the vent? And I said, well, just select a location that's looks nice cosmetically. And so they did. What they did is they looked at the distance between like this baffle and this board, and they centered it right there. It's good. Good job. The problem was the subs that were Ground Zero gave me the subs and for demo purposes, and I put them in there. They sent me like their competition subwoofer. It has like a 2-inch surround, something that that the guys building the box did not know, because all I did is send them the cut sheets. So this is why we have to look at this right here. And this is why I wanted to come back and redo it. Click on this. And actually, let's place it. And now I select done. Now you see the driver's in the box. And this is showing the surround, because this driver has a 1-inch surround. So now let's do this. Let's do the front. Now let's put the vent inside the box. And this is what I had them do. I said, just make it look good. So come over here. You select the vent to preload the dimensions. Click on place. Select the baffle, which they selected right here. To make it look good, they put it over here. Let's see what it looks like on the front. Let's hide that front panel. Okay, so what they did on that particular design, remember, the surround was really big. So imagine like sticking way out here. So when I got the boxes and they didn't have the subs, this is the problem I had. The vent was impacting the surround of the driver. There was no way I could put the vent inside the box, and they already made the boxes. So what I ended up having to do, and of course I took credit for this as part of my demonstration, is we just pull the vent outside the box. And I told the attendees that this box was designed for the trunk of a sedan, and we're coupling it to the listening environment. So it actually worked out. But in your case, what you want to do, you can move this around. You want to make sure that the vent isn't going to be impacting anything. So in this case, now it's not impacting the driver. Let's look at it from the right-hand side. Let's hide that. And it's not impacting the back of the box. So this vent is placed properly in the enclosure. We're not going to have a problem with it hitting the back of the box. It's more than half the vent diameter away from the rear surface and adjacent surfaces inside the box. And then the final step is actually click on done and finalize. Now let's explode this to see how it goes together. And then, we're going on a coffee break, so we just put it here because that looks cool. But then it's time to get to work. So what you want to do next is you come over here to the fabrication page and you print out each of these panels. So top and bottom, 2 pieces. Front panel, 1 piece. Back panel, 1 piece. Side panels, 2 pieces. And side panels are identical in size to the partition. The only difference is the partition has a hole in it. So, if you wanted, you could cut 3 of these. They're identical dimensions. A lot of thinking goes into the way these boxes are constructed. So you have minimum fence movement and you cut these panels all the same. When you put the box together, everything's going to fit. Otherwise, if one of these is off even 1/8 of an inch, you got a gap somewhere. And then you have to fill it in. So, and then if you wanted, you could export that, save that. Here, I'm going to save this as, we'll call this BP4. Okay, so that's all there is to it. But now I want to show you one more thing. Let's go over here and I'm going to clear everything. Normally, if you were to close the program right now and you relaunch the program, it's going to come back to where you left off. But in this case, I'm going to click on reset. That clears everything. I'm going to switch back over here to layer 1. And I'm going to select, let's just say vented box here. In a perfect world, you don't have any constraints on dimensions. So you could come in, select the driver, select the enclosure, design the box, design the vent, do the wood design, cut the wood, you're ready to go. But a lot of times you have to go out to the car and make measurements first. Now, it's really tricky when you have to do that, because remember what I was showing you on the wood design page. If you do anything, if you change these dimensions in a way that where everything is locked, what will happen is it will then change your design, and you end up, as a dog chasing his tail. There's just you go round and round in trying to figure that one out. So here's the way to do it. You go to the car. Let's say we're going to do a rectangular box, just like this. You go out to the car and you take your measurements. The next thing you do is you decide how thick is the wood you're going to use. So over here on options, you can click on that and select the wood you're going to use. Then you use this button here that says Geo. This stands for Geometric Calculator. And I'm going to select a rectangular shape right here and 3/4 inch wood. Now I'm going to take my measurements, say 15 inches by 14 inches by 40 inches. This is a pretty good sized box. So it's telling me that 15 inches high, 14 inches deep, 40 inches wide. The total internal volume of the enclosure that is available is 3.76 cubic feet. But remember, this doesn't take into account the driver displacement or the vent displacement. And let's say in this design, we're going to use 2 subs. So we have 3.76 cubic feet. We're going to put 2 subs in this box and a vent. So, or 2 vents. Let's put in 2 vents. So I know that when I put the drivers and the vents in this box, they're going to take up some airspace. Now, you could be really anal and go in and figure out what the displacement of the drivers are. And it's just a lot easier to save 10%. So in this case, let's pull up. You're not going to see this. I'm going to do it with my calculator here. So I have 3.76 cubic feet. That's my gross volume inside. I'm going to multiply that by 0.9. So I'm reserving 10% for the drivers in the vent. It's a good rule of thumb, 0.9. So my total design volume has to be less than 3.38 cubic feet. I know that if I can design the box with 3.38 cubic feet for the design volume, I'll probably be good. So let's go ahead and try that. So we come over here to Enclosure. First of all, we selected our driver. We already selected the driver. It's that JL audio driver. This time we're going to change to 2 subs. It's a vented box. I'm going to enter 3.38. So I enter 3.38 cubic feet. That's our design volume. That's a response. Now I don't really need to play down here to 25 hertz, 29 hertz. I'm going to raise this tuning frequency a little bit. Does 2 things. Gives me this bump in response and makes it a lot easier to design the vent, because the higher the tuning frequency, the easier it is to design a vent that will fit inside the box. So I'm going to go ahead and change that to 32 hertz. You notice this is getting pretty close to the same design we just did. This time, though, we have 2 drivers, 3.38 cubic foot box, tuned to 32 hertz. Now, we come over and do our vent design. Let's say we're going to use 2 vents. And we really need to make these dudes, let's make them 4 inches. Okay, that's pretty long, but it's probably doable in this box. 2 4-inch ports each port needs to be 15.275 inches long. Now, it gives us a port air velocity of 8.57 inches, 8.57% of the speed of sound. I'd like it to be lower, but that's not bad. And remember, this port air velocity is what happens at full electrical power. So unless you're listening to a 600-watt sine wave, if you're just listening to music, this may not be a problem. So if you're listening at a lower volume, your port air velocity is going to be a lot lower because you're not applying as much power. There's also other factors that go into the vent air velocity. For instance, if the system is mounted behind a seat, the upholstery in the seat is going to attenuate the high frequency harmonic components that are audible from port chuffing. Or if the system is playing at full power, it may be so loud that your ears are distorting. You may not be able to hear the port turbulence just because the system is playing so loud. In this case, let's just say this is good. We're going to accept this. Then we come over and we do our wood design. And, gosh, I wish I would have written down the dimensions. I think it was 15 by 20 or something like that. So anyway, let's say of our 3 dimensions, the one that we can change is the depth. All right, now here's what we know. The design volume was 3.38. The driver displaces 0.21, and the vent displaces 0.211 cubic feet. Now, you'll remember that when I calculated the dimensions earlier, the gross volume, it was 3.76 cubic feet. Now, look what we have here. The total volume of our design is 3.801 cubic feet. That is just like a home run, and that was it's 0.04 cubic feet difference. We're talking a 1/16 of an inch in dimensional variance to make up for that. That was totally by luck. I wished I would have remembered what those dimensions were that we punched in, but let's say that the height was 15, because I think it was like 15. And I think the width, the depth, the width was 40, I think. I can't remember. I think it was 40. So what that does is it tells us that the depth of the box needs to be 14.13 inches long. So what are we going to do? Let's go ahead and place the drivers on this baffle board. So we come over here, we select hole, circular, load the driver parameters, click on place, select the front panel, and use the arrow keys. Let's make this thing. Now you'll see these dimensions. These are the center dimensions. These are the dimensions from the center of the box. I'll show you why that's important. Now, these drivers have like a 1-inch flange. I'm going to move this over to like 7 inches. Now, normally what you want to do, let's do this. Let's make it 8 inches. You want to keep the drivers as close together as possible. And here's why. When you have multiple subs and you put them in close proximity, they have a coupling effect. It's called mutual coupling, and the output actually increases. The other thing is, now it's not such a factor in this case, but if we had 4 subs in this enclosure, the outer 2 subs have a different load than the inner subs, because now you have a boundary on each side. So keeping the subs close together in the center of the box is going to provide better results than if you put them perfectly centered or if you put them towards the outside, because in a system with 4 subs, the loading would be different, and you might encounter a little bit of there might be some phase issues at high sound pressure levels and low frequencies, where you can see the cones actually slowly being out of phase with one another. Anyway, in this design, we're going to keep this sub at this location. It's at -8. Okay, so I'm going to remember 8 inches. I have it offset 8 inches. So I'm going to click on done. And now we're going to place another driver. So I'm going to click on place, select the panel. This time I'm going to make it positive 8 inches. Click on done. Before we proceed, we might want to just look at it from the right. So I'm going to click on right, hide the right panel. We don't have any clearance issues here. So now let's go back to an isometric view. Now what we want to do is place the vents. The vents are going to be a challenge because remember, they're really long. So if I come over here and I click on circular vent, click on vent to load it. The depth is 15.275. In this case, we're going to have a problem with it impacting the back of the box. We have 2 options. We can either place the vents. We can place the vents on the end panels, which I don't want to do. Or you can have the vents sticking out the front of the box an inch or so. Now, right now, the software, the version you're getting, doesn't have a utility that lets you slide the vent in and out of the box and then make adjustments. But in the next version, automated update, you're going to get, it has that capability. So some of this, almost everything I've shown you today comes with the software that is the current version. Let's go ahead and place our vent. So I'm going to click on place and I'm going to click the panel. You can select either the front or the top. Let's see if we can fit it right here. So I'm going to move it up. Make it look nice and neat. Got to be careful because remember, there's a piece of wood up there. So, but you have a flange right here. So let's do this. I'm going to go ahead and I'm going to pull this down. To 11 inches. Click done. I'm going to move this dude out. Let's make it -9. You can do that as long as you haven't finalized the design. So I'm going to come over here, change that to 9. I'm going to change this one to 9. I'm going to just click on that one because I forgot what it was. It was 11. We have to place one more vent. So I'll go ahead and click on place, select the panel. This time we're going to go down to, what was it? $11 minus 7.5, whatever that is. It's like 3.5. And I'm going to go ahead and click on done. Now, like I was saying, in this case, we're going to have a problem. If I click on the top and then I hide it, you can see that the vent's actually sticking out of the back of the box. I think I've shown you guys enough on how you can accommodate things like that by adjusting these dimensions a little bit. Like, for instance, if I were to adjust the width to, say, 36 inches, the depth would grow and this vent would fit inside the box. So here are the things you could do in this particular design. You could either adjust one of these critical dimensions and make it smaller, and that would increase the depth, or you could pull the vent outside the box the necessary amount, say 1 or 2 inches, or you could put an elbow in the vent and make it work that way. Now, speaking of elbows, the software doesn't currently do that, but it's super easy. If the program tells you the vent needs to be 10 inches, that means it needs to be 10 inches measured along the center line of the vent. So if you put an elbow in there, the distance from the end of the port through the center line to the front edge of the baffle would need to be 10 inches. And you guys could do that all day long. So in this case, I'm just going to pretend that I'm going to pull the vent out of the box a little bit. Now, yes, if you move the vent outside the box, technically it does change this vent displacement just a tad, but we're talking, these two vents only take up 0.2 cubic foot in a 3.3 cubic foot box. Moving it out an inch or two is going to have a negligible impact on the design. Remember, box volume variations, 15-20%, almost don't really have much of an impact on the design. The tuning frequency does have a big impact. So in this case, I'm going to just pretend that we're pulling those vents out. So I'm going to click on Finalize. And when I do that, that's what our design looks like, just like that. So now you could send it over to the wood shop, and I've showed you already how to do the fabrication. We'll come over here, just show you. I'm going to save, this is a cool box, so I'm going to save it. We'll call this Sometimes people ask me what I think about individually partitioning chambers. And here's the thing. There's some pros and cons to each, but I typically prefer to use a common rear chamber. And here's why. In a car audio environment, the loading on the front side of the enclosure differs depending on the proximity of the driver to the top side and the floor of the vehicle, the roof of the vehicle, the side of the vehicle. If you have 4 woofers or 8 woofers or whatever, the front loading is different for each sub. But if you had individually chambered woofers and all of those chambers were identical, the back load for each driver would be the same, but the front load varies from chamber to chamber. And in my experience, I've seen phase problems when you do that. One way to address that is if you use a common rear chamber, then the loading on the back side of the cones is the same as on the front side. And so those little variations tend to negate each other. Now, one of the benefits of individual partitions is that you have additional bracing, because when you put a partition in there, it makes this panel a lot more rigid. But you could easily add some bracing to the box yourself. Another advantage to individual partitions is if you have a sub failure or an amp failure, it doesn't impact the system as much as if you have a dead woofer that literally is acting anti-phase to the rest of the driver. So when this one's pushing out, this one's sucking in. If these drivers were individually partitioned, there is going to be a little bit of effect, because when this front woofer moves out and pressurizes the listening environment, it depresses this woofer here a little bit, but it's not near as noticeable as in a small volume like that. So at this point, I think I'm going to switch back over to the camera and see if you guys are still with me. If you like, we can either take a break or we could just go ahead and move straight into the Q&A.